Welcome to the 10th lecture on signals and systems, and the topic is more about Fourier series along with some uncomfortable questions about the existence and uniqueness of Fourier series. You recall that we introduced Fourier series in these terms, that if we have an x of t which is periodic, x of t plus t, then we said that x of t can be expressed as ak e to the j k omega 0 t, k equals minus infinity to plus infinity, where omega 0 is twice pi by t0, with t0 being the minimum t for equation 1 to be valid. And he also said that if to a linear time invariant system, if we put an excitation e to the st to an LTI system, then what we get at the output is h of s e to the st, where e to the st is called the eigenfunction, one eigenfunction of the system, and h of s is the eigenvalue for this particular eigenfunction. Now, before we take up annoying and uncomfortable questions about the existence of Fourier series, let's look at the application of Fourier series in linear system analysis, and this is based on these two facts, namely that x of t, a periodic function, can be decomposed into a number of elementary signals which are exponential, and that for a linear time invariant system an exponential signal is an eigenfunction with an associated eigenvalue. Also, if you recall, h of s is given by minus infinity to infinity h tau e to the minus s tau d tau. This is h of s. This we did last time. Now, in the case of Fourier series, we don't have e to the st, but s is specialized to j omega. Alright, so e to the j omega t leads to h of j omega e to the j omega t. This fact, along with the fact that any periodic function can be decomposed into a sum of exponentials e to the j k omega 0 t, allows us to analyze the response of a linear time invariant system to any arbitrary periodic function. To illustrate this, let's consider a very simple example. Suppose we apply a periodic function x of t to a linear time invariant system whose impulse response is e to the minus t ut. This is a simple RC network. It has an impulse response of this form, and let us find out what y of t, the output, is. Now, you notice that if h of t is e to the minus t ut, then h of j omega, that is the eigenfunction for the system to an, to eigenvalue for the system to an eigenfunction of e to the j omega t, would be integral minus infinity to infinity e to the minus tau u tau d tau, and because u tau is 1 for tau greater than or equal to 0, the lower limit can be replaced by 0, and if you carry this integral out, you will simply get 1 by 1 plus j omega. It's a very simple integral, and therefore for this linear time invariant system, the eigenvalue for e to the minus e to the j omega t is given by 1 by 1 plus j omega. And that's all that I need to be able to analyze the system if the excitation is periodic. To be specific, let us say we apply an excitation 1 plus, let us say, cosine 2 omega t plus sine omega t. Let us say I have this periodic function. Obviously, this is a Fourier series. Can I write the coefficients for the Fourier series? I can write this as 1 plus e to the j omega 0 t plus e to the minus j omega 0 t minus divided by 2j. This is for the sine, and then for the cosine I have e to the j 2 omega 0 t plus e to the minus j 2 omega 0 t divided by 2. So, can I write the coefficients now? A0, let me write in some other color. A0, what is A0? If you look at this, the constant term is unity. So, A0 is 1. Then A of minus 1, that is the frequency minus omega 0. Obviously, the coefficient is minus 1 by 2j. Alright. For A plus 1, the coefficient is 1 by 2j. And you notice that A minus 1 is simply the complex conjugate of A plus 1. This also we proved the earlier day, that is A k star equal to A minus k. Alright. A minus 2, that is the frequency is minus 2 omega 0, and you see that the coefficient is simply plus half. And A plus 2 is also equal to plus half. The complex conjugate of half is half. And the Fourier series is complete. There is no other frequency present. There are only two frequencies, namely the fundamental omega 0 and the second harmonic 2 omega 0, and of course a DC term, and the Fourier series is complete. So, in some cases when the excitation is given, the Fourier series, the coefficients can be written down almost by inspection. Alright. Now, let us look at this and try to analyze the linear time invariant system. The system whose impulse response is e to the minus t ut and whose eigen value h of j omega for an arbitrary frequency omega is 1 by 1 plus j omega. These two are equivalent descriptions, ht to the minus t ut or h of j omega equal to 1 by 1 plus j omega. To this system I have applied an x of t which is equal to 1 plus 1 over 2j e to the j omega 0 t minus 1 over 2j e to the minus j omega 0 t. Alright, I am writing the terms in terms of the exponentials rather than sine and cosine. This takes care of the sine omega 0 t. Then if I write the cosine omega 0 t, half e to the j 2 omega 0 t plus half e to the j e to the minus j 2 omega 0 t. I have not written strictly in the form in the sequence a minus 1, a minus 2, a minus 1, a 0, a plus 1, a plus 2. I have written 1 plus, this is the sine omega 0 t term, and these two constitute the cosine 2 omega 0 t term. Now, because the system is linear and because I have been able to decompose x of t into a number of exponentials, recall that this is also an exponential whose frequency omega 0 is equal to 0. Alright. And therefore, I can write the response by inspection, and that is what I will do. Yt, I will start writing here, Yt, first I find the response to the DC term 1. For this, the eigen value shall be, we put omega equal to 0 here, h of j 0, and that is equal to unity, and therefore this is simply 1, plus, then to this excitation we shall get 1 by 2j e to the j omega 0 t multiplied by the eigen value for omega equal to omega 0, which is simply 1 by 1 plus j omega 0. Then for the second term, minus 1 by 2j e to the minus j omega 0 t, and what I shall here is 1 minus j omega 0, and this process I can continue for the other two terms. And then if I so desire I can combine the terms. You see that this term is the complex conjugate of this term. This term is the complex conjugate of this term. So I can combine the two into a real function. Similarly, for the other two terms also I shall be able to combine, because one shall be the complex conjugate of the other, and I shall be able to combine into a real term. And therefore yt in general shall consist of 1 plus some constant, let's say a1 cosine or sine, I don't know, cosine omega 0 t plus theta 1, which allows for cosine as well as sine. Alright, similarly plus a2 cosine of 2 omega 0 t plus theta 2. This is what I shall get at the output. And you see the analysis, the total analysis did not require any calculation. It is almost by inspection. All that you needed was to express x of t in the form of a Fourier series. And once you do that, then you write the outputs term by term, and that's about all. So this is the ease that Fourier analysis, Fourier series affords for analyzing a linear time invariant system without any integration or differentiation or any complicated manipulation. Let's go back to the series x of t equal to ak. We will come back to this example a little later. Summation ak e to the j k omega 0 t, k equals minus infinity to plus infinity. Now in the example, our x of t was a sum of sines and cosines, and therefore we could easily decompose and identify the coefficients ak. We had a minus 1, a minus 2, a 0, a plus 1 and a plus 2. In the general case, suppose x of t is given graphically or otherwise in a complicated functional form, then how do you find out AKs? Once you find out AKs, the analysis or the decomposition of x of t into elementary signals is complete. Now to find out AK, the procedure is very simple. We will find out AK in terms of x of t, that is the given function, and for that what I do is I multiply x of t by, please follow this analysis closely, I multiply this by e to the minus j n omega 0 t, and so the right hand side also should be multiplied by e to the minus j n omega 0 t. So we shall get e to the j k minus n omega 0 t. Then I integrate the left hand side over one period. Because x of t is periodic, it does not make sense to integrate it over any length of time more than a period, because the integration shall also repeat, and therefore I integrate from, let's say, 0 to t0, where t0 is the fundamental period. I can do that, or else I can change the lower limit to some arbitrary constant, let's say a. Then I must add an a here. In other words, one period, where you start and where you finish, is absolutely immaterial. The integral should be the same, and such integrations, that is integration over one period, we don't write the lower limit and upper limit. Usually what we do is, instead of writing the lower limit and upper limit, we simply write t0 here. Below the integral sign we write t0. That is, let me write it again, t0, this does not mean lower limit. Whenever we write like this, it means that you integrate the function over one complete period, dt. Is that clear, this nomenclature? this saves some amount of writing. So this should be equal to summation k equals minus infinity to plus infinity ak. Now if I integrate with respect to t, obviously the integral sign can be taken inside the summation, isn't that right? Because the summation is over integers k, and small t is a continuous variable. It has nothing to do with k, they are independent of each other. K is an integer variable, small t is a continuous variable. So I can take the integral inside the bracket, integration e to the j k minus n omega 0 t dt. Agree? This has also to be integrated over one period. Alright. This integral is extremely important because we will keep on getting this again and again in our development. Let's look at this integral a little carefully. The integral that we are worried about is over one period e to the j k minus n omega 0 t dt. By Euler's relation, I can write this as integral t0 cosine of k minus n omega 0 t dt plus j integral over one period sine of the same thing k minus n omega 0 t dt. Alright. Now if you integrate a sine function over one complete period, what is the value? What is the area under the sine curve over one complete period? It is 0. It is 0. What about the cosine function? It is also 0 except for k equal to n. Except for k equal to n. And therefore this integral shall exist only for k equal to n. And under that condition, integral t0 e to the j k minus n omega 0 t dt shall be equal to t0 k equal to n. Otherwise it is 0, k not equal to n. Alright. Now let's go back to the previous expression. You recall that this is a summation, this is an integration within a summation, and the summation index or the summation variable k occurs inside the integral sign also, and this integral is 0 unless k equal to n, and therefore the total summation shall exist only for k equal to n. For any other value of k, it is 0, and therefore the total summation would be simply equal to an times t naught. That t naught comes from the integral, which gives me an expression for an. An is therefore equal to 1 by t0 integral over t0 e to the power, I beg your pardon, x of t e to the j n omega 0 t dt, where I made a mistake, it should be minus. This is the expression for the coefficients of the Fourier series. Let me recall that the Fourier series is if x of t equal to x of t plus t with capital T0 as minimum t for this relation to be valid, that is the fundamental period, and omega 0 equals to 2 pi over T0, then x of t can be written as ak e to the j k omega 0 t, k equals minus infinity to plus infinity, where ak, the coefficient, is given by 1 over T0 integral T0 x of t e to the minus j k omega 0 t dt. This is the complete statement of Fourier series. Fourier series, Fourier's theorem says that a periodic function x of t, till we encountered those uncomfortable questions, we are very happy to state that a periodic function x of t can be expanded in this particular form, where omega 0 is the fundamental frequency, k omega 0 is the kth harmonic, and the coefficients ak are given by this expression. Let's look at a few examples to introduce another two terms which we shall have to deal with. Let's have first a simple example. Let's say x of t is simply equal to 1 plus cosine of omega 0 t. Well, obviously this is a Fourier series in which a0 equal to 1, a minus 1 equal to how much? How much? A minus 1?
Minus 1 by 2j.
Why 2j? Cosine omega 0 t does not require a j. And a plus 1 is also equal to half. So you know the coefficients. Okay. Now in other words, my x of t is equal to half e to the minus j omega 0 t plus 1 plus half e to the j omega 0 t. I have just repeated this. Now if I make a plot, 1 I have written, that is the a0 term. I have written plus 1. Hasn't it come in the monitor? It is there. Now if I plot ak versus k, mod ak versus k, ak's in general could be complex. For example, if I had a sine, then the coefficients would have been 1 by 2j and minus 1 by 2j. So ak could be complex. If I plot the magnitude of ak versus k, and another plot is angle of ak versus k, these two plots go by the general name of a spectrum. These two plots, the coefficients versus their integer indices, this shows what is called a spectrum. And this spectrum, if I plot the magnitude, is called the magnitude spectrum, or more commonly as the amplitude spectrum. Amplitude spectrum. Whereas this, the angle versus k, is called the phase spectrum. And Fourier series leads to what are known as line spectra, exactly like optical phenomena. Here we do not have a continuum of frequencies. Time is continuum, but the frequencies are multiples of omega 0, omega 0, 2 omega 0, 3 omega 0, and therefore these ak's exist only for discrete integer values of k. So if I plot magnitude ak versus k, what we shall get is a series of lines, and therefore the spectra that we get is called a line spectrum. Alright. For example, in this particular case where x of t is equal to 1 plus cosine omega 0 t, our spectrum shall look like this. This is k, 0, plus 1, minus 1, plus 2, minus 2, and so on. And our spectrum simply looks like this. We have 1 here, that is the DC term. At minus 1 we have half, and at plus 1 we have half. Notice and remember that this is not a time, this is not a signal sequence, it is not in the time domain, it is in the frequency domain. That is, what k equal to plus 1 means a frequency of omega 0, k equal to minus 1 means a frequency of minus omega 0, and this means a frequency of 0. So although we are plotting versus k, the abscissa here represents frequency. It is not a time domain sequence, it is not an x of n. We represent x of n also the same way. And sometimes to distinguish between time domain sequence and frequency domain spectrum, we omit these dots at the top. That is, we simply draw a line of corresponding height, 1, half and half. This is the amplitude spectrum of this periodic signal, the other values being 0, okay, plus 2, 3 and so on and so forth, they are all 0. This is the amplitude spectrum of x of t equal to 1 plus cosine omega 0 t. If I want to draw the corresponding phase spectrum, well, what is the phase spectrum? Yes. What is the angle of A0? Obviously 0. The angle of A1 0, and angle of A minus 1 is also 0, and therefore it is 0 throughout. This is the plot of angle of AK, which also sometimes is written as phi k versus k. Once again, it is a plot of phase or the angle of each coefficient versus the integer variable k. Amplitude spectrum and phase spectrum are adequate to describe any periodic function. Exactly like, if you know the periodic function itself, of course you know it, but it can alternatively be described in terms of the amplitude and phase functions, because if you know them, you can go back and reconstruct the given periodic function. Let's take a little more complicated example. Suppose my x of t is, let's say, cosine of twice pi t plus sine of twice pi t, let's introduce a factor half, plus let's say 1/4 cosine of 4 pi t. Alright. Now obviously the fundamental frequency here, omega 0, is equal to twice pi, alright, and capital T0, the fundamental period, is equal to 1, alright. And to determine the spectra, I first write it in the form of the Fourier series, that is, I write x of t, you correct me if I am wrong, I am doing this by inspection. Cosine 2 pi t I can write as half e to the minus j 2 pi t plus half e to the plus j 2 pi t, then excuse me, plus 1 by 4 j e to the minus j 2 pi t plus 1 by 4 j e to the j 2 pi t minus. Which one? This one or this?
This one.
Okay, this is minus. Then plus 1/8 e to the j 4 pi t plus 1/8 e to the minus j 4 pi t. Now let's write down the coefficients. What we have is a minus 1 is equal to half. Alright, I think we require this again. A minus 1 is the coefficient of the frequency term minus 2 pi, and therefore it shall consist of this term and also this term, alright, these two, and therefore my coefficient shall be half minus 1 over 4j. Similarly, a minus 2 I have no problem, it is this term 1 by 8, okay, 1 by 8. I have no problem in writing a plus 2 is also 1 by 8. Can I write a plus 1? Well, before that, a minus 1 minus 2, a plus 1 would be half plus 1 over 4j. I didn't have to look at it again, because if I know a minus 1, I know a plus 1, because they are complex conjugates, provided x of t is real, that is right. And the only other term remaining is A0, which is equal to 0. So let's try to draw the spectrum. Now for the spectrum, you shall have to find out the amplitude as well as phase. The amplitude of this term would be 1/4 plus 1/16, all right. And the angle shall be, I can write this as, let me do some manipulation right here. I can write this as J, and this sign we can take as 4, all right. So tan inverse imaginary part, that is 1/4 divided by half, which is equal to 1/20, no, I beg your pardon, 16 and 5/16, square root of 5/16, it's not legible. This is equal to square root of 5/16, that is the amplitude, and the angle is tan inverse, how much? Half. No minus sign. I had corrected that minus, it was minus 1/4j, I took j up, and therefore the minus sign became plus. This is the amplitude, this is the amplitude, and this is the phase. Now you can do this for all others and then make a sketch of magnitude and phase. Magnitude versus k, you must identify k. K has only 3 values here, 0, 1 and 2. Similarly, there are -1 and -2. So in this spectrum we shall have how many lines? 5 lines, of which one will be 0, that is A0 term. Similarly, in the phase spectrum, how many non-zero terms shall we have? Just 2, because A2 and A-2 are also real, and therefore their phase is 0. Now would it have been possible for one of them to be negative? Suppose there is an AK which is equal to minus, let's say, 1/16. What would you say about the amplitude and phase of this term? Obviously amplitude is 1/16 and the phase is pi. Now is it plus pi or minus pi?
The same.
It's the same. Okay, we will face difficulty. If we answer like this every time, then we will face difficulty, and I will take that example. I'll take that example to show you what the problem is. If we consider pi and minus pi to be the same. All right. Let's take this another example of x of t. Now look at this carefully. This is one of the most useful waveforms in electrical engineering and also in computer engineering, of course. 1, 2, 3. Okay. There is a repetitive wave like this, and to be specific, let's say this is my t axis and this is x of t and this is t equal to 0. It is a repetitive, it's a periodic function. Let us say this is capital T1 and this is minus T1, and let's say this is T0 by 2, then this shall be minus T0 by 2. Obviously this can be considered as one period, from minus T0 by 2 to plus T0 by 2. There is nothing sacred. We could have taken from 0 to this point. What is this point? T0, simply T0, because it repeats, it repeats from here. Now this is the basic period, one period. We take this as the period because the integration will be somewhat simpler. It has symmetries on both sides. In other words, within one time period, I can describe x of t as equal to keep life simple, let's say the amplitude is 1. Let's say the amplitude is 1. Then x of t is equal to 1 for small t less than capital T1. Is that right? For mod t less than T1. Is it okay? I have described both sides for positive t and also negative t. And it is 0 for mod t lying between T1 and T0 by 2. This is one way of expressing periodic functions. Is there any question on this? No. This is periodic, so let's try to find the Fourier series. Now, to determine, that is, I write x of t as summation ak e to the power j k omega 0 t, where omega 0 is of course 2 pi over T0. That is the fundamental frequency. We have identified T0 here, and so we know the fundamental frequency. K equals minus infinity to plus infinity. Now I require this waveform. Now as far as the DC part is concerned, that is k equal to 0 term, k equal to 0 term. Now you notice that k equal to 0 term shall be simply the average value of the waveform over one period, that is minus T0 by 2 to plus T0 by 2. Because if you write the general expression for AK is 1 over T0 integration over T0 one period xt e to the minus j k omega 0 t dt. Now if k equal to 0, you notice that this term will become unity, and what we shall have is the area under the curve xt dt over one period then divided by the period. So it is the A0 is therefore the average value of x of t over one period. And if you look at this waveform again, you see that A0 can be calculated by inspection. It is simply twice T1, this length is twice T1 multiplied by 1, that is the area, and that shall be divided by T0, and therefore the average value of the function is twice T1 by T0. Alright, let's find a general AK. A general AK shall be given by 1 by T0 integral minus T1 to plus T1, because inside one period you notice that the function is 0 from minus T0 by 2 to minus T1 and T1 to T0 by 2. So all that is required is to integrate from minus T1 to plus T1. Let's do that. X of t is 1 e to the minus j k omega 0 t dt, and this integral is extremely simple. Its value is given by sine, let me write on another page, AK is given by sine of k omega 0 t, sine omega 0 capital T1 divided by k pi. And here we had assumed that k is not equal to 0, right? For k equal to 0 we had evaluated the term independently just by looking at the function. Let me point out that this is valid also for k equal to 0, that is, it is valid for all k. For k equal to 0 it is of the form 0 by 0, and you know L'Hopital's rule, by which you differentiate both with respect to k and put k equal to 0, and then you get exactly twice T1 divided by pi for k equal to 0. Alright, so you have found out the AKs, and if I now want to draw the amplitude and the phase spectrum, let's see what difficulty shall we encounter. You notice that AKs are real. They are real. Now a real quantity, what about the phase of a real quantity? It's always 0? It's 0 when it is positive. When it is negative, the phase is pi, plus or minus, and that's where we enter the difficulty. First, let's draw AK without bothering about the separation of amplitude spectrum from phase spectrum. We simply draw AK. It's a real quantity, either positive or negative. We should be able to draw it. Let's say we draw AK versus K. Obviously, we shall get a series of lines. We start with K equal to 0. This is 2T1 by pi, and then K equal to 1, maybe we are somewhere here, then K equal to 2, and so on and so forth. Alright. Now, if I draw the envelope, and since x of t was real, the amplitude spectrum shall be symmetrical, right? A minus 1 is simply the complex conjugate of A plus 1, and therefore the magnitude should be the same. In other words, the amplitude spectrum shall be an even function. Now here it turns out that if we do not care about amplitude and phase, it's the same story. It is symmetrical on both sides, and then if I draw the envelope, it goes like this, exactly like that of a sine wave, because it is indeed a sine, except that, yeah, the amplitude shall be decreasing. That is, it is of the form sine x by x, and as k increases, the amplitude decreases. This becomes a it's kind of a damped sinusoid. The envelope becomes a damped sinusoid. Now, if from this I draw the amplitude and the phase spectrum, alright, what shall we get? The amplitude spectrum would be like this. We are drawing the amplitude spectrum, so we don't go negative. We flip it. We get something like this, then something like this, then something like this. And this is what repeats on the left hand side also. And so my amplitude spectrum shall look like this. We shall have a line here and lines here. And so on. I have not drawn exactly to scale, and the number should be the same here, and so on. This would be the amplitude spectrum, that is AK versus K. What about the phase spectrum? If I draw the angle of AK versus K, what would be the envelope of the phase spectrum? Now obviously in this range AKs were positive, and therefore in this range the angle shall be 0. AKs were positive, the angle shall be 0. Now in this range AKs were negative, and they were negative here also. Alright, so what do we use? Both plus pi or both minus pi? That is the question. Now we have a problem. The problem is this: magnitude must be even. Magnitude has to be an even function. That is, if f of x is a magnitude function, then f of x must be equal to f of minus x. On the other hand, the phase is an odd function. That is, phi of x is equal to minus phi of minus x. So if you take this as minus pi, then this should be taken as plus pi. Is that clear? That's how it becomes an odd function, not otherwise. So what we shall have is this: these lines shall all be plus pi, and these lines shall all be this shall all be plus pi, this shall all be minus pi. On the other hand, if you take the other way, if you take the other way around, that is, if you take this as plus pi, then you must take that as minus pi. But that is also not arbitrary. It shall be decided by the given function x of t. It is not arbitrary, it does not depend on you. Whether it is plus pi or minus pi can be determined by taking k approaching a particular value here, that is, let us say 3 minus, and then finding out what the angle is. These delicacies and these sophistications we shall enter later, but let me point out that whenever a quantity, a real quantity is negative, the phase is not necessarily plus pi, it could also be minus pi, and there is a difference between the two. The difference is this, that when you draw a circle, you can go to plus pi. Suppose this is your radius vector and you turn rotating in the anti-clockwise direction. You could go to pi like this, or you could go to pi like this. The end result is the same. The paths are different, alright, but the sign of the ultimate angle depends on which route you take, whether you take anti-clockwise or you take clockwise. It shall matter. This spectrum is an extremely important spectrum. Sine of k omega 0 t1 divided by divided by k pi. I can write this as omega 0 t1 divided by pi sine of k omega 0 t1 divided by k omega 0 t1. Can I? I have introduced a omega 0 t1 here, and this pi I have taken out, and you see that this is of the form sine theta by theta, except for a multiplying constant. It is of the form sine theta by theta or sine x by x, which looks like a damped sinusoid when plotted versus theta. It is an extremely important spectrum, and you shall encounter this again and again, whether you take control or communication or whatever it may be. Now let us go back to Fourier series. Fourier series says that x of t is equal to summation ak e to the j k omega 0 t. And let us raise some uncomfortable questions to start with. We have already seen, without any rigorous mathematical arguments about existence, we simply derive that ak is equal to 1 by t0 integral over t0 x of t e to the minus j k omega 0 t dt. Implicit in this statement is the fact that we have presumed ak to exist. How do you know that one or more of the ak's may blow up, they may go to infinity for some k? Suppose there is a specific ak which goes to infinity. This integral goes to infinity. Well, then does the Fourier series exist? Obviously not. Alright. Number 2. Even if ak's are finite, they are nicely behaved, positive, negative or complex quantities with definable amplitude and phase, even if that is so, how do you know that this summation will converge? It may or may not. The summation may diverge. These are the uncomfortable questions about Fourier series, which Fourier refused to consider while giving his series. These questions were raised by his examiners, Dirichlet in particular, P.L. Dirichlet and Laplace, and that's how Dirichlet made a contribution to Fourier series, which we shall discuss a little later. But for the present, let's assume that the Fourier series exists, and let's say in the Fourier series k equal to minus infinity to plus infinity ak e to the plus j k omega 0 t. Let's say we have an infinite number of terms, doubly infinite. We have infinite number on the left, infinite number on the right. It's a complicated waveform, it's a periodic waveform, so we require infinite number of terms. Now an engineer cannot work with infinite number of terms. He cannot spend the rest of his life counting AKs. So what he does is, he makes an approximation. He says, okay, enough is enough. We know from practical experience that AKs diminish. The amplitude diminishes with k, and therefore let's truncate this series. Let's truncate this series at, let's say, k equal to minus n to plus n, ak e to the j k omega 0 t. This is truncated x of t as an approximation to x of t. All right. We cannot take infinite number of terms, so we take a finite number. Let's say we truncate at 10. Minus 10 to plus 10, and therefore we have 21 terms in the Fourier series. 21 because there is an A0. And therefore in doing this we encounter an error. Let's call this error as En of t. Then En of t, the error is x of t minus xn of t. This error in general, if x of t is real, then this error shall also be real. Is that correct? If x of t is real, then xn of t is also real, and so the error shall be real, but the error could be positive or negative. On the other hand, if x of t is complex, then the error is also a complex quantity, and it shall make sense to calculate its magnitude. All right. The magnitude is also calculated. Magnitude is calculated for another different reason. The reason is that if it is real, the error could be positive or negative. So what we do is we calculate En t magnitude, and we calculate its square. All right, which simply means that negative and positive. Well, we could have taken the magnitude only. That also takes care of, but I am going to give you a different error criterion, and for that purpose I squared this. And then what I do is I integrate this over a period, and I call this En. All right, that is, this is the squared error, the integrated squared error. I have taken the square of the magnitude of the error, and then I have integrated over one period, and therefore this is the integrated squared error. And if I divide by T0 now, it is the average squared error, or what is known as in mathematical language mean squared error. Mean squared error. En is the mean squared error, and it makes sense to calculate only over one period, so we say mean squared error, and then we minimize this. That is, we choose AKs. What are our variables? AKs. We can choose AKs in such a manner that En is minimized. All right, and the result is a very interesting result, which we shall discuss next time.